So I'm going to switch to a different set of slides, but this is basically what we have done. So this is a sort of recap of what we have done, and then some details that I'm going to talk about before we get into the place where we left off last time. So I just want to backtrack a little bit, remind you what we were doing. So we're looking at these, let's say I had this data, Titanic data, and then we wanted to do a probabilistic prediction problem, or like perform a prediction of this variable survive based on some of the covariates. So far we have used this binary sex variable. Today we're going to also look at adding more features. So the variables that we use for prediction, they're called features or covariates. This is called target or the response. So what we talked about was to model this joint distribution as a general joint distribution, and then figure out what would be the optimal classifier if we knew this joint distribution. Okay, that was the start. So what we want is a function of the predictor, or sometimes called predictor, sometimes called features, sometimes called covariance. A function of that, which I'm calling as y hat, so that y hat is almost close to y. We want to see what is the best we can do if we know the joint distribution. That was basically the majority that we spent the majority of our time doing that. Okay, so let me remind you, assume that we have this joint distribution, and first looked at the majority rule classifier. Hopefully you remember what was that, and then we looked at the distribution that that it is. So we basically end up showing that the optimal rule would be this. So look at the probability that y is not equal to b given x, and then try to maximum for a fixed x, try to maximize what is the decision that maximizes this probability, either 0 or 1. If it's 0, then I'm going to predict 0. If it's 1, I'm going to predict 1. So this came because we set a loss, if you remember. So we had the 0-1 loss, which is 1. If our prediction does not match y, then 0 otherwise. And the expectation of this loss, which we call risk, sometimes you might write it as the risk of the classifier. You might see me write something like that, maybe. So it depends on the function that we pick. It would be a number for the classifier. So that turns out to be, for this loss, turned out to be R of f, which is the expectation of the indicator, y hat not equal y. This turns out to be the probability that y hat is not equal to y. Okay, so that's this classification rate, the probability that is classified. And we did the argument, and it turned out that the optimal rule minimizes this so-called posterior risk. This is, can think of it as just this, but conditional on x. That's posterior, given that we see the data. Posterior to see the data. That's something called posterior risk, which is equivalent to maximizing 1 minus. This is actually 1 minus. Right, this is 1 minus probability of y equal d given x. So minimizing this is equivalent to maximizing this quantity, right? So that would be equivalent, and this is what we have here. So the optimal decision rule for the 0-1 loss, or for this classification rate, basically, is the thing that, or the rule that looks at the conditional probability of y given x and chooses the label that maximizes that conditional probability. So we all of this we've proven, and in our case it turned out that this beats the majority rule classifier. So this is, people remember this, right? Questions? So now I just want to point out this extra step. So we did this all for a discrete random variable, which was just a binary feature, whether someone is male or female. But this exact argument works for a general covariance. Suppose x was a general, maybe continuous random variable, maybe a vector or something. So this probability of y not equal to y hat, that's my risk. I can decompose it as a probability of y not equal to f of x conditional on x and times the probability we observe that particular x. So this is a fancy notation from measure theory, which I definitely don't expect you to know. But this is like, if you're not comfortable with this, this is like a simple notation or fancy notation for writing px dx. This is like the probability. This is the density of x, let's say. This is roughly the probability that I observe something close to x. So that replaces probability of, so replaces, if you go through the argument, replaces the probability that x is equal to x, because for continuous variables, this probability usually is 0. So we have to break it into, again, conditioning, but now we have many choices, infinitely many choices, so we average a sum over all of them, which is going to be the integral. So that's the integral. This part, which is the marginal probability of observing something at x or near x, is out of our head. That's the feature. The joint distribution dependent on marginal probability. This one I can choose. And conditional on x being little x, this is going to be deterministic f of little x. And this is my choice. I can pick it to be 0, or I can pick it to be 1. I'm going to pick f of x to be 0. If I put 0 here, that makes a smaller value for this than if I put 1. So if you go back to your argument that we did, we plug in 0 and 1 here, and whichever one is smaller, we pick that choice for that particular x. So that would give you back exactly this. So if you think of this as f of little x, you can think of this like that. This would exactly be the analysis that I would do here. I'm going to choose the decision here that minimizes this guy over here. So this argument is general. If you think about it, I can go into more details if it wasn't clear. But just go back to the thing that we did with the x being just the 6 variable. There it was just 2 cases. The sum had 2 terms. Now we have infinitely many terms. We have an integral, but the basic idea is the same. Just for every x, you have to minimize this. And if I do it for every x, then the whole thing is going to be minimized. It's just average of all the small things. The least ones for every x. Okay, so the prescription for optimal under the 0-1 loss is the same. And there is an exercise in the notes that I sent. I don't think I assigned it, but you can go through this argument even for a general loss function. And it's really easy if you generalize this. So this would be the expectation of the loss, and here would be the expectation of the loss conditional on x. And it can determine what the form of the optimal rule is. It's just a minor tweak. It wouldn't be that, but it would be the minimizer of the posterior risk in general. Okay, that's all I wanted to add here, that this rule is valid no matter what the underlying feature is. And you're going to do some homework problems for the continuous variable and so on. And later on, we'll do more continuous variables. But for now, just keep in mind that this argument is general. We know the structure of the optimal rule for this classification rate or the 0-1 loss. Sounds good? Okay, questions? Okay, one more point. This one I believe I assigned as a homework problem. So what we can do is we can simplify things a little bit. So because there are 2 choices and these 2 choices are not independent. Suppose I'm looking at this equivalent 4. If I pick 0 and 1, if I plug 0 and 1, these 2 values are not going to be independent, right? So if I know 1, I can determine the other one. Can someone tell me why? So if I, for example, plug in 1 here, I have to look at these two values for a given x and decide which one is smaller or bigger, actually in this case, to decide the decision. So these values are not independent of each other. I just need one of them to determine the other. Why? Yeah, because the sum is equal to 1. So I just keep one of them. Let's say I'm going to look at this for every x. How can I get the other one? 1 minus that. So now suppose I have this and 1 minus this. Which one is going to be bigger? Like suppose I have like p and 1 minus p. When is going to be p bigger than 1 minus p? I have p between 0 and 1 and 1 minus p. When would p be bigger than 1 minus p? When p is greater than 1/2. And if it's less than 1/2, then 1 minus p would be bigger. So I can rewrite this decision by just looking at this and threshold it at level 1/2. Okay, instead of trying to compare the two, because the other one is 1 minus this one, I just look at the value of this, and look at it, compare it with 1/2. If it's bigger, my decision is going to be 1. If it's less than 1/2, my decision is going to be 0, because then this would be the bigger one, right? So that brings us to this idea of defining this quantity. That's exactly what I have here. I'm going to call it eta of x. And you're going to argue in your homework problem that this is exactly the expectation of y given x for a binary variable. So that's why it's called a regression function. It's in regression in general. The expectation of y given x is called a regression function. So this is going to be a function of x only, because we're averaging y over all values of, not over all values of x, but given the value of x. So this is going to be a function of x. And this is the last part, but in any case, I'm going to call this eta of x. And you can see that the decision rule, and I basically argued part A for you. If you go back to the problem, hopefully you can write this down. The decision rule is going to be 1 if eta of x is bigger than 1/2, and 0 if eta of x is less than 1/2. So that's equivalent to this rule that I have written here. So I can, instead of working with these two probabilities, I can just keep one. Which is going to be eta of x for us, and this is going to be rather important for us throughout. And it also connects classification and regression. So optimal rule in binary classification, when the variable is encoded as 0, 1, right? Under the 0, 1 loss, can be obtained by looking at that regression function and thresholding it to level 1/2. What happened for x, I'm not determining what happens if it's equal to 1/2, and that's what you will think about in your homework problem. What should I determine? Like, what should I do if for a value of x, it turns out that eta of x is equal to 1? So that's basically so in our case, if you remember, in the example that we did, this is just going to be, just take two values. We did this calculation. Let's go back. Yeah, you can see it here. So this guy basically 0.72 and 0.19. So my regression function here, if I want to write it, would be 0.72 if x is female and 0.19 if x is male. That's just two values. And then in each case, I'm going to go and compare this with 1/2. If it's bigger than 1/2, I'm going to declare 1. If it's less than 1/2, I'm going to declare 0. So this is bigger than 1/2. So decision is 1 here. This is less than 1/2. This will be 0 here. So it's the same idea, but rather simple. You don't have to worry about the two cases. Okay? Sounds good. So you now have three different versions of the optimal rule for this classification under 0, 1 loss. Later on, we're going to come back and see what we can do if x is not continuous. But this is an important function, regression. Okay, questions? So all is good, except that we don't know the joint distribution. Remember, this was the original assumption that we made. We don't know this. Okay. So anyone remembers what we do in practice? Somehow we want still to like use this machinery that we developed in practice. So yes.
When you're given data,
Right. So test and training, we're going to come back to it later today. But let's say I'm just given the data. I'm not going to worry about training. So you're looking up a little bit ahead. But let's say I'm given the data, right? So we want to estimate that probability of joint distribution from the data, right? And so if you remember, the joint distribution for us was, in this case, the simple case, determined by 4 numbers, which is the probability of these cases, each case having this exact combination of these covariates. So now I can use the data to estimate these probabilities. So how do we do that? Do you recall? Let's say I want to do, which one is harder here? So let's say this is like 10 rows out of 982 rows. I'm showing 10 rows, but the total number is 982 rows. And let's say I want to estimate there are 4 numbers, but I want to estimate, let's say this we call y, this was x. Probably that y is equal to, let's say, here there are a lot of, let's say 1 and 0. And x is male. So I'm going to put a hat here because it's going to be an estimate. So how should I compute the estimate? Like, what is a reasonable estimate? We did this last time, right? So I guess you already meant. So what was your name again? Sorry. Alex, yeah, okay. So what was that? Yeah, but they're not 10, so they're more than, right. Yes, that's fine. So you look at all the cases that are 0 and male. Let's say if there were really 10, if this was all the data, let's say, then, so 1, 2, 3, 4, 5, 6, right? So if this was all the data that we had, it would be like 6, and then what? 6 can't be a probability, right? So divided by 10. So that would be like 0.6 roughly. It's interesting, let's say. Is this going to be, so in our case, this is close to the actual estimate. So male survived, not survived. So 0.52. It's actually not a bad estimate, even based on a sample size 10. But in general, because you have more data, you're going to go count how many cases of this exact combination of covariates you have divided by the total number. This is like the empirical estimate. This is the natural thing to do, right? How many, this is like the frequentist interpretation of probability. What is this probability? Like the proportion of observing this exact combination of data, the approximate. So if I want to be mathematical, I would write this like 1/n summation I from 1 to n, indicator yi equals 0, xi equal m, right? In our case, even our estimate is an estimate. This is an estimate of our whole estimate, which you can compute if you have the entire data. So that's the fancy way of doing it. If you recall this indicator notation, this is saying that this is, so here I have a training set x1, y1, x2, y2, dot, 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 x and yn. So each one, so this is, for example, I equal 1, this is I equal to 2, dot, 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 I equal to 10, right? And so this would be yi, this would be xi. So each one of these rows will contribute one of these observations. So this is my sort of, let's say, training data, if you will. My entire data could, we'll call it the training data, let's say. That's what I use to form my estimate. And for each one, I'm going to go and check whether they match this exact combination of covariance. If it is, then it's going to be this one, it's going to be 1, otherwise it's going to be 0. So when I sum, I'm basically counting how many cases, how many i's, how many rows this exact combination occurs. Right, so this is basically that count. And then 1 over n, so the n is the total number. So this is the sample size. Right. So this is our empirical estimate. Empirical estimate of the population probability y equals 0, x is equal to m, based on a training data of size and sample size. So if you're a machine learning person, you'd say training data. If you're a statistician, you'd say a sample size. And training here means I'm going to use this data basically to train my classifier, to learn the classifier, which in our case starts from learning the distribution itself. Okay. Does that make sense? Notation is clear. This mathematical notation is helpful to write these things, which you probably intuitively understand, right? But it's helpful because then I can also do the same for writing the conditional. For example, now I want to compute the conditional distribution of y0 given x is equal to m, or y equal 1 given x is equal to m. Right? So I can do this for all the combinations. I can change the combination. So what I would get is all the 4 numbers. So what will happen? Is this clear? So what if I want to compute, let's say, the conditional probability of y equals 0, given that x is equal to m? We actually need these things to calculate the optimal rule. Maybe actually 1, but because we did the 0, let's do this. How do I get an estimate of this quantity? Yeah. I believe we also did this last time, but just, yes. I'm going to also use the empirical probability of x equal to m because I also don't know that, right? But I'm going to have an estimate of it. So this one, we calculated it roughly 0.6 based on 10 rows, let's say. So how about the other one? What should I do with this? Let's say there are 10 rows. What is the estimate of your probability of being male? What do we do? Right, count how many rows of male in that column and divide by the total number. So how many do we have? Like 1, 2, 3, 4, 5, 6, 7, 8, right? Divided by m. So this would be 8 divided by 10 is 0.8. So this would be roughly 6 divided by 8. Someone maybe can calculate this. 175. Right. 2/3. No. 3, 4, 4. Yeah, you're a good engineer, I guess. So engineers can do this. So 0.75. Then, so if I want, is this clear? Okay, that's the same idea. I just marginally count all the cases. Another way of writing this is formally, if I want to write it, can anyone tell me how to write it like this mathematical form? So if I want to mathematically write it, how should I do it? 1 over n, I'm going to help you. Sum I from 1 to n. Indicator, yeah, 1. Xi equal to m. Yes, exactly. So this just counts how many cases. I'm going to go look at all the rows. I just care about the xi's. If xi is equal to m, this is going to be 1, and this just counts how many of those we have. And then we're done. Right. By the way, this 0.75 is interesting. So these counts I get from the bigger version of this data, even bigger than 982. And 0.75, if we go back, the probability of being 0 in male would be 0.81 based on the table. Those probabilities I estimated based on like 1,100, like 1,300 examples. And even based on the 10 sample size of 10, we got a pretty good estimate, which is not that accurate. But as you will see, this doesn't change the optimal classifier actually. So what will happen is that's actually another good exercise. So we might be able to recover the optimal classifier in this case, even based on a sample size 10, as long as those probabilities are bigger than 1/2. I think the threshold, because the threshold, I don't care about. So for example, from this, I get that p hat y equal 1 given x is equal to m is also approximately 0.25, right? So my decision for the male case would be what? It would be 0 because this is bigger. Or you can say that this is less than 1/2. So we're going to pick 0. So our decision would be correct. Although this probability is not exactly the right probability. This probability, this should be like 0.81. This should be 0.19. If you observe many more things, but it doesn't change the nature of the decision because they're still on the right side of 1/2. This is still bigger than this. So my decision for the case x equal m is still that they don't survive, right? Do you understand this? So there is a lot, the classification is a lot easier task than, for example, regression. In regression, I want to recover this probability accurately. In classification, I don't need the exact probability. I just need it to be like on the right side of 1/2. Binary classification. We'll see this more and more later. Does that make sense? So based on this calculation, out of this data, I could like figure out what my decision has to be if I'm just going to do based on sex. And like if it turns out to be male, for the female case, I'm going to do the same, right? You can count, and then it's a good exercise for you to do this on this. See if the decision for the case x equal female changes or not. It seems that it might change because like, you have very few, like 2 samples basically, effective sample size. Another way of like doing the conditioning would be, I like this, we're going to stick with this, but another way of doing this would be just go and the cases where x is male, just count how many females, sorry, how many cases survive. Just those rows for which you don't have to like separately do the joint and the marginal. So just conditioning means I'm going to go only in the cases where I have male here. I'm going to look how out of those, how many are survive. That would be my prediction. And if you do this calculation, that would be equivalent if I write it. So remember, we have, so if I plug in this formula here, this is 1 over n summation I equals 0, xi is equal to m divided by summation 1 over n. 1 equal x equal to m, xi. And you can see that these two cancel out, right? So once you cancel out, you can see this is counting how many cases of male you have, and this is saying within the cases of male, how many cases of female you have. So this calculation that I just did is in my head, or you probably do, is you can also see it if you write it in formula. So you don't have to, the entire data set doesn't matter, only the cases. So this is, because this is here in both numerator and denominator, you're just working on the examples for which this is true. Here I'm just counting all those examples. Here I'm just counting examples for which this is true, and also this is true. Right, so the ratio of these counts give you the conditional probability. Okay, it's just exactly mathematically follows, and also intuitively it should be clear. That's what conditioning is doing. Okay, does that make sense? Okay, good. Everyone happy? I redid this. We did it last time, but another time because some people are not comfortable. Hopefully, it makes sense. So it's like mathematical version of writing what you understand intuitively, and this formula is going to help us like build more complicated classifiers later. Once you understand what is going on here, you can see the more general pattern emerge. Right? Okay. Yes.
I'm sorry, I know this kind of does get into the homework question, but like for the Titanic example with the females, it's 2 cases, 1, 0, 1, 1.
Yeah.
If you were to then have to randomly pull a female, I know that is essentially the homework question, but like there's no way to determine which one's what. So you just put randomly one, essentially.
That's a good question. So it's exactly what happens here. So if you do for the female, with this is actually a good. I didn't intend this exact 10 row, but for the 10 row, you can see in the female case, if I want to determine this p hat, let's say y equal 1, given x equal to f, right? Our estimate would be, if you understood the second argument, I'm going to look at the cases that are female and then count how many survive. So 1 out of 2 survives. So our estimate would be 1 divided by 2. So this is 1/2. This is exactly eta of, let's say, female, right? Or so we would have to compare this with 1/2, and here is exactly 1/2. So what should I do? It's like equally probable to be survived or not survived according to this data. So that's what you have to determine. Right? It's worth thinking about. I can give you the answer, but it's worth thinking what happens. What would be the criteria? The criteria is the accuracy, right? I care about the accuracy. So does it matter what I do in terms of the accuracy or the risk? Think about it this way. So if there is a choice that improves the accuracy or reduces the specificity, that's the choice. If not, then tell me what we should do. Okay. But good observation. So this has all the like interesting features by accident. Okay. So you can see this case is actually not, in this case, our estimate of this is not quite good, because if you go back to the actual true distribution, in this case, this turns out to be 0.72, we're off. We're off so that we hit the boundary. So we're off catastrophically. So if it was like 0.65, okay, but there are too few samples. So based on sample size 10, you could figure out the other case, but based on sample size 2, sample size is small. Yeah, I'm not going to talk much about it because I want you to think about it. Questions? All clear? Okay, so now, so that's basically all written again. Here I'm writing those things, but with x and little x and y as the placeholders for 0, like this was 0. Sorry, 0, 1, and this is like male, female, all these combinations you can put here. And you can see this argument works as long as your response, and our response for now is going to be binary. But let's say the covariate could have more than 2 levels. Let's say if I did P class, which will be next, it has 3 levels. So if I do three levels here, it's still the same estimator works. There's going to be like 6 combinations. I can compute this for all the 6 combinations. This is going to be my marginal. This is going to be my estimate of the conditional probability. Okay, that's the summary of what we did. And I have a little bit here of justifying. So law of large numbers here. So what I'm saying is that by the law of large numbers, basically this is a good approximation. So let's see how many people know what the law of large number is. Large number, law of large numbers, sometimes called LLM, law of large numbers. Have you seen it in previous class? Yes.
I think in the 102C the most probable class.
Okay, 102C.
Yeah. So when the n is large enough, it kind of gives you an accurate approximation.
That's good. Yeah, that's exactly what this is saying. Based on the law of large numbers, this is a good approximation of the probability. This is like good approximation of P, the population Y equal Y, X equal X. But you didn't tell me what exactly is. So the conclusion is correct. What is it? Did they, okay. You haven't seen it in 100A? I'll be correct. What was your name, by the way? Okay. Can you say it? Okay, I'll ask you after class. Yeah. My ears are not that good. So what was the thing that you learned in 100A? The question. So probability, right? What things did you learn? What was the topic of 100A? Not this. Okay. It's like not law of large numbers, no central limit theorem. Did you see it already? Been a while, but you have seen it, right? Is that okay? No one remembers what law of large numbers is. Yes. Right, so let's say I have an IID sample from a distribution, right? If for the sample mean, large number says that as n goes to infinity, this converges to what? The expectation, the population, the expectation of Z under this distribution. It goes to the mean of this random variable. Right, that's the law of large number. It converges in various senses, like almost sure, like in probability in distribution, like any very strong sense converges to that. And you can do it in practice. For example, if you have a coin flip, you flip a coin many times, and you take the average of the number of heads. Let's say how many times it comes up heads divided by, and so this is like Bernoulli. If you remember what the Bernoulli is, Bernoulli theta is probability that Zi is equal to 1 is theta, probability that Zi is equal to 0 is 1 minus theta. That's a Bernoulli random variable. The expectation of each one is theta, right? 1 times theta plus 0 times 1 minus theta. So in this case, the average, so you're modeling each coin flip as a 0 or 1, and so either heads or tails, let's say heads is 1, for example. And then I observe a bunch of zeros and ones. I take the average, so this tells me how many ones I have divided by the total number. And this is going to converge to the probability theta. So usually one estimate the probability that the coin is coming up heads, for example. And that's how you do all the things in basic statistics. So what I'm trying to say is that sort of now rings a bell. Does that make sense? So if you have a sequence of I here, and this is one of the two fundamental problems, the theorems in probability, this and central limit theorem. If you take two things from probability, like intermediate level probability, one is the law of large numbers, the other is the central limit theorem. Now we'll see whether we're going to see central limit theorem. But this is saying averages, empirical averages converge to population average or population mean or expectation. That's like, this is what it says. As the sample size grows, if you have IID samples. So why now this? I'm sort of arguing that this converges as n goes to infinity. As your training set, the size of the training set grows, this gets actually a better and better estimate of the p. This converges as the sample size grows to this. And I'm claiming that this follows from the law of large numbers. So anyone can say why that is. So it seems like the law of large numbers, the way that I presented it is about expectations, not probabilities. But here I'm claiming that the same law is implying that this converges as n goes to infinity to what we want, which is the population probability here. Anyone can see the connection? Is there a connection between expectations and probability? It is. Okay. Yeah. So what is the definition of expectation? There is an integral, but let's say simpler than that, let's say. Like intuitively. For discrete ones, let's say there's no integral, just a sum, right? Suppose I have a random variable that takes values 1, 0, with probability p, with probability, like we did the theta. P here. P. So we did p 1 minus p. So this is the Bernoulli value. So what is the expectation here? Expectation of y. One, so expectation is like a weighted average of the values that a random variable takes, with the weights being the probabilities. That's like the intuition. Sometimes it's an integral, sometimes it's a sum, but it's just a weighted average of the values that you take, where the weights are the probabilities of taking those values. So I'm going to have to average these two with these probabilities. So p times 1 plus 1 minus p times 0. You get p. Okay. So you can see the connection between expectations and probabilities for a Bernoulli variable, it's a binary variable. The probability of it being 1 is just its expectation. Okay. That's by definition. Now, can you see the connection here? Can anyone tell me why I'm saying that this converges to this by the law of large numbers? Yeah, I saw it. Yes.
Is that because of like when n is large enough, the sample size will approach to the population?
Not the sample mean converges to the population mean. Okay, so this is a sample mean of what?
Because the sample size when is like almost equivalent to the population size, the mean of sample is the mean of population.
Can you say that this statement is, can you say your statement again?
So like when the sample size approach to the population size, the mean of the sample
Right, our population, let's say, has infinite. So basically the population, there's no sample size for the population, right? Population is these probability distribution. So imagine infinite. So as n goes, the sample size goes to infinity, let's say. I translate that as statement. Then the sample mean goes to population mean. So that's exactly the law of large numbers. The population mean is just expectation. The sample mean is this, but what is the connection to this? So this side, there's no expectation or population mean. There's a probability there. Is my claim correct? I'm claiming that this is an instance of that. So this is actually a good estimator. As your sample size grows, this is going to converge to what you want. You would like to check that. This is sometimes called consistency. If you have taken 100B, this is a consistent estimate of this quantity. Because as the sample size grows, it converges to what it has to. Anyone tell me? The reasoning is just one line based on what we had discussed. Yeah. Who was that? Yes. The expectation of no, so yeah, so the expectation of this the expectation of probability would not be zero. So this is some expectation, if you want to claim it. So let me help you. So this is some variable zi, fixed little y and little x. So this is a variable zi. These are IID because these samples, these rows are independent and have the same state. So this is a very newly variable because it takes only value 1 and 0. So this is very much like this setting. And so this, by the law of large numbers, converges to the expectation of zi. Doesn't matter which I, because they all have the same distribution. So what is the expectation of this? It's a binary variable. It takes value 1. With this probability, it takes value 0 with 1 minus this. So the expectation of this is just exactly this guy. Right? This is just an instance of this problem that we have. So you're just taking the sample mean of a bunch of Bernoulli variables. Here, Bernoulli is this indicator. And so this is the sample mean converges to the expectation, but the expectation is just the probability. So the link between expectation and probability is this indicator function. So the indicator of the event, if you take the expectation, it will be the probability of that event. Okay. So the law of large numbers give you that this converges to that as well. Okay. Again, the reason is this is the sample mean, the sample like an average of like empirical average of a bunch of Bernoulli, like these are Bernoulli variables if they take value 1 or 0. Looks complicated, but in the end it's either 1 or 0. And for different i's, they're independent and they have the same distribution because x and xi, yi's have the same distribution. So these are so zi's, IID, with some probability, and then the expectation. So this converges to the expectation. The expectation happens to be the probability of this being 1. Each one has the same probability. So it's like a coin flip. Basically, you're flipping the coins. It comes up head with this probability. And I'm taking the average convergence. Expectation, which turns out to be the probability. Okay. Good. So this was not needed, but it's good to connect. So there's a little bit of theory that this estimator is a natural estimator based on the law of large numbers. Again, this is going to be by the law of numbers and the same argument. This is going to converge to PF x equal to x. Okay, again, these are indicator values converge to the expectation of this is going to be just the probability. I'm doing x because this is like it could have xi here, but the probability doesn't depend on I because they all have the same distribution. This is like a generic x has the same distribution. So x1 up to xn and x are distributed similarly. They're IID from the marginal of that capital P. Okay, so that reasoning is clear. Okay, it took us a lot, but it's worth like knowing. And then there is a little theorem that I can't use the law of large numbers here because this is not an average, but there's I don't know if you have seen it, or maybe if you go to graduate school, you'll see it, because this is sort of a continuous function, because the top is defined by 1 over n. This is converging to probability of y equal y and x equal to x, and this is also converging to this. The ratio has to converge to the ratio, and then the ratio is exactly the conditional distribution. So this is like follows. from something called continuous mapping, if you want to check continuous mapping here. But this is not necessary. It's a continuous function. If you have ratios of two things, and this is converting, the denominator is converting to something non-zero, and the numerator is converting to something non-zero, then the ratio has to converge to that, and this is just a conditional distribution. So this is also a consistent estimate of the conditional distribution. So everything that we're doing is consistent, which means as n goes to infinity, as I gather more and more data, I'm going to converge to the true thing. Assuming that the IID assumption holds, assuming that the rows are homogeneous, basically, which sometimes in real data application doesn't hold. That's our basic assumption. Questions, comments? Okay, we have done all this. So now this is our estimator, which is, this is p hat. Now, used to be p, now it's just p hat based on that. So it's either that, or you can say that f hat is, if you followed what we did, it's going to be eta hat x if x is bigger than 1/2. Sorry, it's going to be 1 if eta hat x is bigger than 1/2. 0 if eta hat x is less than 1/2. And you're going to tell me what happens for the other boundary case. And this is just p hat y equal y given x equal x. Or I can just do like this, capital X. So this is my regression function. So remember the regression function is this. I'm just going to put a hat here and a hat there. So if I put a hat there, this is an estimate of the regression function. So I now have an estimate of the regression function as well. So put a hat here, that would be my estimate. And so I'm doing the hat here. So this would be my estimate of the optimal rule. I just have to plug this like a plug-in estimator. Just plug in my estimate for eta into this, and then we're done. Right? Or plug it into here, and you're done. This is sometimes called the plug-in estimator. If you hear it, plug-in estimator. No, I should move it here. These terminologies are helpful if you run into plug-in estimator of the optimal rule, optimal Bayes rule. Plug-in means I look at the structure of the optimal rule, just plug in my estimate of whatever needs to be estimated in there. So eta x is what we need to estimate. I'm going to plug it in here. Or in this case, this is what I need. So I plug in. It used to be this. Without that, I just plug in the estimate, and then now I have my rule. So and we did it sort of early on in the example. We actually did the decision rule, right? So you calculate this, right, and then you figure out. So if this is bigger than 1/2, based on this, you decide. We did the decision. But this is the formal way of writing. Okay, sounds good. So that's what I mentioned can be used in practice. So you estimate your joint distribution and the conditional distribution, or you can say the regression function. Regression function is just this for a particular value of y. So I don't need the two cases, as I mentioned. I just need one of them. So you can say that this is just, we can write everything again, like summation I from 1 to n, indicator yi equal now 1, xi equal to x, divided by summation. This is a little bit boring, but just that's it. Okay, so that's my regression function, and I just care about this case. And then once I have this, then I can form my plug-in estimator. These are both the same thing. Sounds good? That's how you do it. So it's very practical. When you have like discrete covariates, let's say, few levels, this is a very useful thing to do. You can do this, you have a good estimate of the Bayes rule. You don't have to worry about, oh, I need to do logistic regression, or I need to like kernel neural nets, like 10 layers of neural nets. You don't need that. So very simple, right? And very close to optimal if you care about this classification range, right? So I can repeat this procedure, for example, if you understand, if I want to include this line, this covariate as well. Everything that we did works out. Now my x is going to be this, right? This x is going to be the entire thing. So now my x is going to be a vector. I can call this xi1, this xi2, and the entire thing would be xi. It has two coordinates, but nothing changes. So this xi will have, it's a discrete variable. It takes how many levels? Not two, but not three, but not four, more. The first one takes two possible values. The second one takes three. I didn't mention this, but this belongs to 1, 2, 3. This is like the passenger class. 12, it's a little too much. 6, yeah, so 2 times, so this takes two values, this takes 3, so this, let's say, vector variable, this takes 2 times 3, which is 6 values or levels. So this is now a new, you can think of it as a new covariate, okay? A new covariate that takes 6 values. You can encode it however you want. It doesn't matter that there are 2 coordinates. It's just like one column, but now takes 6 values. And I can repeat this process. I will have a joint distribution. This joint distribution is now not going to be, so my joint distribution is not going to have 4. So here is going to be y. Here is going to be what? Like that xi, or like, yeah. So let's say xi1, xi2. Now this is going to have 6 levels. Male class 1, male class 2, male class 3, female class 1, female class 2. So like 1, male 2, male 3, female 1, female 2, female 3. And then here I'm going to have like 0, 1. Now I have like 12 is now the entire joint distribution determines by 12 numbers, right? So I'm now going to estimate all of them. The way I'm going to estimate is exactly like that from the data. And then I have the optimal rule, like close to optimal, plug-in optimal rule, right? So you can do it for any discrete variable, right? Or a combination of discrete variables, because it boils down to another discrete variable with higher number of levels, larger number of levels. So if I have 2 discrete variables, you can treat it as a new discrete variable with the number of levels being the product of the levels of each one. So everything that we did sort of generalizes to like many discrete covariates. Okay, does that make sense? So you can easily add this. Adding age would be problematic because it's not discrete. We're going to talk about this, but I can easily incorporate this new feature, right? I get a new joint distribution. Now it's described by 12 numbers, which is like 2 by 2 by 3. 2 is the number of levels of y, 2 is the number of levels of this, and 3. So 12 is the number of elements of this, right? So 2 by 2 by 3 numbers. But you're going to go there and you're going to calculate all these probabilities, and then you have your optimal, right? Good. I guess you can do it, right? So if I give you the data, you can go implement the optimal rule for this. So questions? So this is like a little bit of like R code, which is in that note that I send you, like partial book basically. So I'm not going to go into details of the code, but this basically does the counting for that entire 900 or so rows. This calculates that conditional distribution, this guy. And basically just does the counting, and this is divide. So this gives you the conditional estimate. So that's the conditional estimate of survive. Basically, that's your regression function. So this is eta hat x, which is p hat y equal 1 given x. So here x being female, this is that, and then so it takes two values. And based on this is very close to what I gave you as the population level. This is based on 900 rows. And this is probability. This is basically p hat of x equal x, right? And then based on this, you can write the classifier. And this classifier can be summarized. This you can do in R without doing this calculation. This is like by hand, sort of. But there's this package rpart, an rpart plot, if you're interested, produces these nice plots. I have a little bit of code in that book that I linked. So again, what this is done, it just summarizes everything that we have. So what this is saying is, if I go, if I have, this is x equal to male, this is x is equal to female, and these numbers are those conditional probabilities of survival. This is just this 19 here. If you do the plot, this 19 is that, and this 0.73 is the other one. So that gives you a nice a compact way of doing it. Actually, a representation of this. And here it's just going to be the probability. This is unconditional p hat of y equal 1. This is conditional probability of y hat equal 1 given x is male. This is, sorry, hat here. This is p hat of y equal 1 given x is female. And this is the unconditional probability. So this determines the majority rule. So you compare this number with 1/2, it's less than 1/2, our decision would be 0. So this is the majority rule without considering any covariance, we do 0 here. If you stop here, that's our decision. If we want to include the next, this variable, we're going to come down here. And in this case, our decision would be 1 because this is bigger than 1/2. And here it's going to be 0 because it's less than 1/2. So this is a graphical way of representing things nicely. So this single picture summarizes both the majority rule, estimate of the majority rule, and the sort of optimal or plug-in optimal rule based on a single covariance sex. Right? And these percentages are how many, which fraction of the points end up being here, or the observations, basically these marginal counts. So this is the probability. Sorry. What this other one is, this is our p hat of x equal f. This is p hat x equal male, and 100% is just everything is here. Okay, good. So this is a simple example of decision trees. We may see more complicated, like when you have covariance, but now you know what decision trees are. Sort of basically, at least in the discrete case, it's a pictorial way of representing these type of rules, not necessarily the optimal rule, but in this case, turns out to be the optimal. Okay, good. Now, I'm going to come back to this slide. This is another exercise which I haven't probably assigned. I can come back to that later. We're going to add the P class soon, but I just want to go over the chain test that Alex also mentioned. So, or maybe let me, just let me mention. So how do we know the majority rule is not better than this. We did it at the population level. We compared the accuracy at the population level. But remember, we don't know, if you go back to our calculation, the way we decided that including this feature sex is better, or like it's the thing to do, is by comparing the accuracy and the risk. Okay, but we don't have the access to the accuracy. So what should we do now? Now that we're estimating everything from the data, how should I compare? Anyone? This is a little bit tricky, right? So we know how to estimate these probabilities from the data, right? I know this. Now, like we argue this is reasonable. The way to do it is by using these empirical averages. There's a very strong reason for doing that, which is the law of large numbers. Can I also estimate the risk or the misclassification rate using my data? Because I still don't know the actual distribution, right? So if you go back, let me just remind you what this is. So this is where we started doing the calculation for the risks or misclassification rates, right? And you can see that this can be done if you know the joint distribution, right? So these probabilities, so this is the probability of marginal probability of y equal 1. These are these conditional probabilities, and now we have estimates of all of them, right? I have estimates of all of these. So can you suggest, can I compute the risk? Or like this classification, can I get an estimate of this classification rate as well? Can I do a plug-in estimate of this classification? Yes, no. Can I do these calculations now based on my data? Yes. How? Yes.
Can you split your data to a training exercise?
I don't want to do that, let's say. Can I do it without doing that? I just want to see why would I want to do that? Can I do it not without, can I do it without splitting? Do we need to split? You know that you have to split probably, you've seen, but I just want you to arrive at that conclusion at some point. Is it really necessary? I've been giving you the data. You have used all your data to calculate your classifier, like estimate the classifier, but computing these probabilities. You now have a good estimate of the joint. You have a good estimate of the optimal rule. Now, can I use the same kind of argument to estimate these risks? There's a simple answer, which may or yeah.
Assign a new column, say that this is now going to be your expected value, and then go check if it is.
Expected value, assign columns to.
Like, you say like, oh, okay, we expect for row 1 that's going to be 0, and then you can say check if that equals 1.
Oh, okay. So yeah, right. So you know the actual y, right? So okay, so that's the that's a good way of doing it. Let me give you one example. The answer what I was sort of suggesting was to do plug-in estimate here, because you know the p's, but you know p hats, so you just put hats here everywhere. I have estimates of these, all of these, and I can put hats there and there and there and there, and I can calculate these numbers. And if you do it, it turns out to be very close to these numbers because I got it from a bigger sample. So it turns out that if I put a hat here, I have estimates of these. I can plug them in, right? And I get an estimate of misclassification rate. This would be equivalent, if I'm not wrong, to what Alex just mentioned, which is just go. This is much simpler. So we have a classifier. To measure accuracy, we can do this. So I can go, I plug it into my classifier, it produces a y hat, right? There's a function, takes xi, outputs a predicted label, and I compare it with the actual label. If it matches, I have 0, 1 loss. So it matches, I don't pay any price. If it doesn't, I pay a price of 1. And I just go through everything, and then I take the average. That would be my estimate. So if you do this, that's how you do it. This would be, if I'm not wrong, you can check, equivalent to what I mentioned, the plug-in estimator, because the way that we constructed that is based on these counts, actually. So that's a hard way of doing it. This is an easy way of doing it. That would be, if you do that, so just bear with me a little bit. So that would be this calculation. If I want to do it mathematically, now I understand this notation, I'm going to go over each row. I apply my classifier to xi at row and compare it to the true yi. So this would be y hat I, my estimate or my prediction. And if this is not equal 1, I pay a price of 1. If it's equal to 1, I don't pay a price, and then I sum and take the average. So this would be my approximation. So approximately, it's approximating p. It's actually not a good approximation. I'm not going to write it. But this is supposed to be an approximation of the misclassification rate. This is called the training error. Okay, so you're computing the error based on the original sample that you use to calculate your estimate. Okay, everyone understands what the training error is. So I have my training data. I now train the classifier using that data. I can now go and predict. So what is my prediction for each one of these? Example, it's not going to be exactly equal to yi, because my prediction is very simple. And so I count how many errors I make, and this is going to be empirical. So this is going to, we want to claim that this is going to converge to the probability sort of f hat x I not equal to yi, but this is not going to converge to that. So this is going to be a biased estimator. It's going to underestimate the real risk. And I want you to think about why that is, and that's why you do the training test. In this case, actually, it doesn't matter much. You'll see the training and test error would be very close. So this is actually a good estimator in our case. But there is a reason why we don't use, you can use this, but this is going to often severely underestimate, especially later on, you'll see when the classifiers become more complicated. So you're going to be too optimistic about your error. Just think about it maybe next time, tell me why. You can also cheat, look at stuff online or what I posted. Think about this, okay? It's important. Any questions? Thank you guys. Let's hope